Welcome to the shop. Well, the parts are all complete. They've been plated, anodized, powder coated. Everything is ready for assembly. And in this, the last video in the series, I'll be putting one together. So here goes. First thing to do, and let me get this little camera moved here. Okay, first thing to do, the powder coat, the holes in this piece are cut fairly precisely for a press fit with the bearing, and if I just try to jam the bearing in, I'll have a bad time at the press because the powder coat kind of interferes with the precision fit. So I use the Noga deburring tool to scrape away the powder coat and prepare for pressing. Now, as I said in previous videos where I was using the tool post grinder to grind down the outer diameter of the shaft, that I wanted to make sure that the bearing fits nice after plating, and this plating is fairly thick. It's surprisingly thick, and sure enough, it's a little bit difficult to get it on the end, but sure enough, the bearing fits perfectly with just about no slop, so the amount of grinding was correct. So put a little paper towel on the press to protect the powder coat, and nice press fit. Someday I probably should make a proper stand for this arbor press where it's actually bolted to a table, but for now, just kind of struggle with it. Okay, so that's pressed in. Now I'm going to go over to the storage room and grab some feet. My storage room is right next to the assembly area, so it makes it kind of convenient for me. And I'm gonna grab a seat here. So it's kind of convenient for me to go get parts. I use Loctite. Number 243, it's blue Loctite, slightly improved formula over 242. And all screws are secured with Loctite, which makes them a little bit annoying if it's ever necessary to disassemble anything for maintenance, but it definitely does keep them in place during normal use. This Loctite, this blue Loctite, the dye that they use can really be a problem if it gets on the yellow powder coat. It tends to stain it, so I'm very careful here. Got this paper towel, and I always wipe the Loctite off my finger. So here we have a powder-coated base, and it's looking pretty good. The powder coat, I think I've said this before, The powder coat looks good, but it's not what they call a Class A finish in the automotive world. It's, it's good enough for a glassworking bench, and I've seen what they look like after a couple of months of use, but yeah, it's as good as it is. I'm gonna go get a tool. Nice having everything so close together. So next thing I'm gonna do, these holes were fairly precisely made on the machine, but plating sometimes builds up a little bit of extra material. So just gonna quickly run a reamer through it and grab a couple of pins. And let me demonstrate here. This magnet bracket goes thusly, and make sure that I'm kind of doing this blind. I really can't see what the camera sees because it's up against the wall. The magnet bracket mounts to the main axle, and it should have a little bit of movement that allows the magnet to drop down when it's de-energized. And I try to mill these as perfectly as I can to try to minimize the amount of movement so the magnet doesn't have to jump up into place when it is energized. And this one is pretty close, but I like to get even closer. So the axle has a threaded opening for a little set screw, and it's got to go in kind of backward here, so I stick the tool through the hole, dab on a tiny bit of Loctite, and then reverse thread to get it in. Then take the second set screw that holds the little pin in place, get that excess Loctite off my finger. So now the second little set screw goes thusly, and let me get the orientation correct here. Pin is just a piece of 1/4-inch steel rod, zinc plated from the manufacturer, and fortunately they provide the material in the correct size, so even after plating it is the correct size. So you can see here what happens, I don't know, maybe you can see, that when I tighten the little set screw, I get a little bit of adjustment here, and of course when the Loctite cures, the adjustment is kind of fixed in place. So I'm going to tighten down the screw that holds the pin in place, and then this part is ready. And by the way, I strongly recommend T-handle hex drivers for all NQALHA owners. I really dislike, oh, this one fits even better. That's just about perfect like it is, but I'll still put in the set screw. Maybe it'll loosen up over time, I don't know. I really dislike the style of hex driver where it's kind of like a Swiss Army knife that has all the hex keys all folded up into a body. And yeah, I guess the argument is that, well, you always have your full set with you and they don't get lost and yada yada yada, but as far as I'm concerned, they're just a pain in the ass to use, because the handle always gets in the way, the hex drivers themselves are too short, and especially when working on the NQALHA, there's a lot of places on the NQALHA where you need a longer hex driver to get into where you need to get in. So there we have, and that one looks really, really nice just the way it is. It probably doesn't need very much, if any, adjustment at all. So back to the screw storage. I probably, if I was maybe a little more prepared, would bring all the necessary screws out and set them on the bench, but it's so easy just to walk into the storage room. So 5/16 bolt, or screw I should say. Actually, technically speaking, I believe it is a bolt, but you typically call them a shoulder screw. Anybody that doesn't want to use the steel base and wants to screw the NQALHA directly to their bench, well, it's a standard screw and it's a fairly heavy screw. So next step here, I'm going to be mounting the magnet plates, and in order to do this, I needed to make a special tool. Fortunately, when you have a machine shop, making special tools is easy. So, had to make a special tool because with the bearing pressed in place, there's no way to fit a regular end wrench in place. It just doesn't quite reach, and so this offset wrench allows me to grab the nut while I tighten the screw. So I'm going to prepare all of the screws with Loctite. .1032 by 3/8 flathead. In most cases on the NQALHA, I use socket screws, but for this application, because the magnet needs to slide over the surface of the plate, I got to use a flathead screw. And for the front screw, a regular wrench works just fine. And of course, while doing this, I'm always checking my finger and wiping on the paper towel to make sure that I'm not getting blue stains all over my nice new parts. And there we have it. Back to the storeroom. In the first version of the NQALHA, the magnet plates didn't have these little protrusions sticking out, and this allowed the arm to be rotated beyond safe limits. It allowed the arm to be rotated so extremely that it broke the conduit. And that's one of those things where when I was designing the prototypes, I always just knew the limits of the machine and never over-rotated. But as soon as I released it to the general public, I discovered that, oh yeah, people who don't know the secret will over-rotate it and break the conduit. So version 2 introduced these extra little threaded tabs on the magnet plate with these 1032 socket screws, and they are travel limiters, stops. So it is now pretty close to impossible to go beyond the limits and break the conduit. So there we go. My bench isn't precisely level, and you can see what's going on. These ball bearings are so good that because my bench isn't level, it kind of like takes off and goes where it wants to. But, and of course, here's demonstrating the stop where it hits right there and it hits right there, and that's as far as it can go. During assembly, I'll just put a little clamp on the thing because I kind of want it to stay in place. Now, the vertical arm axle is held in place by a lock collar. And of course, I'm putting Loctite on the screw. This guy comes from the factory with a smooth face, and if that smooth face was allowed to rub against the bearing, you'd get binding at the top race of the bearing. So I put it in the metal lathe and cut, I don't know if you can see it on the camera, cut a little bit of a recess here to provide a little bit of clearance. You know, that fits so nicely. So there we go. And I give it just a tiny, tiny little bit of space, 50 thousandths or so. So there we are. And it's back to the storeroom. Going to be preparing some more flathead screws for mounting magnet plates. The magnet plates are made out of steel. Well, they have to be steel because magnets only stick to ferrous metal. And steel rusts. So I wanted to protect the magnet plates from rust. In the first prototypes, I just used bare steel because, you know, only prototypes, they weren't really going to be around that long. But then when it came time to do production, I thought, well, what can I do to protect these parts? And my first thought was zinc plating. But it turns out that zinc is a fairly soft metal, and the magnets dragging along the zinc kind of caused a little bit of problem. So I switched to nickel chrome. Chrome is a very hard material, and it's actually the face of the magnet itself is chrome-plated steel. So chrome against chrome seems to work pretty well. I do see some small evidence of very fine scratches, but the magnet does seem to slide nicely. Also, in the later versions, starting with version 2.1, I've introduced hinged magnet holders on all axes, so when the magnet is de-energized, it has a chance to kind of like hinge away from the magnet plate, and this appears to work very well. This is a somewhat interesting situation here. The vertical arm has a hinged portion, which has got a very small amount of motion and a little pin in it, but I want to be able to retain this pin. And in order to retain the pin, there's not really any room to put in a threaded set screw, so I end up, I can't do this during the machining operation. I have to do this in the assembly operation. Take it out after the pin is in place, the part is assembled, put it in the bridge port and drill a hole all the way through, tap it, and put a screw in. And this holds it securely in place. I couldn't just put a tapped hole in the aluminum because there's not enough room there. It's just a fraction of an inch and there wouldn't be any thread to grab onto. So I'm going to head off to the Bridgeport and I'm going to do this one and also going to do the twist axis as well. And yeah, the fit is very nice. Almost no slop, making sure the orientation is correct. So I'm off to the Bridgeport. I've already zeroed the machine, set the zero at the rear corner, left rear corner, using the Heimer indicator. Then I take the same tooling plate that was used to make the part, and then I've got two different size spacer rings here, and a 1/2-inch socket screw, just lining this up by eyeball. It doesn't have to be precise, within a fraction of a degree. And then this is going to be, I think I got a little bit of crud on the drill bit. Going to be drilling for a 632 hole, and did I mention I don't like 632 holes? I'm running on generator. We have a power outage, and the power cycling on and off seems to have confused the computers and confused the network, so the computer is not responding to anything, so I'm gonna have to start over again. Okay. Fortunately, I have a good generator. Allows me to continue to make progress during these power outages. So, using the Heimer to determine the zero position, then start the servos, do a sanity check, and verify that it goes to 0. Of course, I could probably just drill this hole by eye and it would be fine, but if I have precision available, why not? Why not be precise anytime you can? So there we go. Very carefully tech drilling. I don't want to break a drill or a tap while doing this. So there we have the first part, and then they use different size magnets, so the vertical arm uses a larger and stronger magnet than the twist axis. There we have it. Holes. I'm always a tiny bit nervous about tapping with a 632 tap. They are a pretty difficult little tap to deal with. Unfortunately, they're very common. The 640, which is probably the correct, if you were just being theoretically correct and not being concerned about availability, the 640 is probably a better choice, but they are so obscure that you just about never see them. So I'm going to tap this guy by hand. I'm very experienced. Oh. I'm very experienced doing power tapping with the cordless drill, but the 632 tap just makes me nervous. So plenty of tap magic. Careful, careful, careful. Breaking off a tap at this point would be a really, really bad thing. And yeah, maybe I shouldn't use a tapped hole here. Maybe a little spring roll pin would be a better choice. But I haven't broken a tap yet, and I've had great success with these parts. So just be careful. Careful, careful, careful. Lots of back and forth motion to break the chips. Using a spiral point tap that ejects the chips through the hole. It's a good tap to use for through-hole tapping. When I'm power tapping, I use a spiral flute tap, but the spiral flute is substantially more difficult to use by hand. So there's a successfully tapped hole. Constantly being careful here to wipe the grease off of everything, because I'm dealing with finished parts now, and I'm going to try to keep as clean as I can in order to guarantee that the Loctite is able to do its job. I'm going to wash down this part with alcohol after the tapping operation and make sure that I'm started straight. A little more tap magic. I'm being very, very conservative. I'm giving like a quarter turn, maybe a half turn into the material, and then multiple back and forth cycles. So, another part successfully tapped. Okay, the parts have been tapped and cleaned, and I'm going to put in their screws. But actually, before I put in the screws, we'll go ahead and get the Loctite primed up here. Need to press in the bronze bushings. So, make sure everything is nice and clean. Make sure the screw recess is in the right place. Look at it, make sure I'm doing everything on the right side. These holes in the aluminum were reamed to get a really nice press fit with the bronze bushing. And yes, they do get a very nice press fit. Let me make sure it seats all the way. And then look at this one to make sure that it's in the correct orientation. I don't like pressing my bearings in the wrong direction. Might as well do the lower arm as well. So there we have it. And now, take the screws, trying to be very aware of where the Loctite goes. Are my fingers clean? Is there any excess Loctite squeeze out grease? Because these are finished parts and I have to be substantially more careful at this stage than during machining. Okay, so the arms are, oh, need to get an adjuster. Okay, got a number of things to say here. The bottom arm is, it goes into a slotted hole, and in back of the slotted hole is this little block, and the little block can slide back and forth in the slotted hole. And the reason for this is that it's possible that some guys, or some glass workers, I shouldn't say guys, some glass workers want to use the NQALHA for precisely pressing a Maria onto a graphite, flat piece of graphite on their glass working bench, and they would like to have the axis of the NQALHA actually precisely perpendicular, so they get a nice perpendicular Maria. And by using the two little set screws that protrude thusly, it's possible to move the bottom arm in and out slightly to help dial it in a little bit better. And when used with a precision square, you can get it pretty darn close. So the axle mechanism here is a bronze bushing, a shoulder screw, and these shoulder screws are ground and they're fairly precise. And then on the other side is a Teflon washer. I was unable to find a commercial source for these guys, so I ended up making them myself, which isn't that horrible. I mean, I wish I could find a commercial source, but they weren't that bad to make on the Bridgeport. And I didn't show that operation because just too simple. So when I tighten down the screw, I get, it's not a 100% loose, it's a slightly tight fit, and I like this because if this movable joint was too loose, if they were all too loose, everything would kind of be loosey-goosey all over. And I like them to start out a little on the tight side, and then as they wear in over time, they get a little bit looser. But I don't like this axis to be absolutely loose. I think the horizontal axis, I love having that on ball bearings because that one should be effortless. But in use, it kind of is a little convenient for the vertical axis to have a tiny little bit of drag, not much. And of course, controlling that, keeping that under control is a bit of a trick because we're dealing with some really tight tolerances. It really is a matter of thousandths, the difference between loose and tight. And you know, the aluminum stock has tolerance. That's nice. The aluminum stock has tolerance, the Teflon has tolerance, the bronze bushings have tolerance, and so it's really hard to get it within a thousandth. I'm using a nylock screw, a nylock nut on this end to capture the screw in place. This 1/8" piece of metal is just too thin to be threaded, and the shoulder screw, the threads don't go all the way to the end anyway, so even if it was threaded, you wouldn't get very much thread engagement. I'm gonna go get some more bronze bushings. Once again, the reamed hole in aluminum results in an excellent press fit. No problem at all. So these oh, there goes the generator. These screws get a little bit of Loctite. Make sure I don't have a chip on the little Teflon washer. Yeah, fitting together very nicely, very precisely. I'm gonna inspect these Teflon washers to make sure that they don't have any contamination. That one had a chip on it and needs to be a really smooth surface. Getting this last one in is a bit tricky. And then I need to line up the hole in the washer. And that one started out a little tighter than I'd like, but then after exercising it a couple of times, it kind of like got itself under control, and now it feels good. So I'm going to start assembling the head pivot. Another little set screw, magnet plate, and then back to the storeroom. Yeah, probably for the next one of these, I'll just bring all the screws out. A lot of walking to the storeroom. So this is a bit of an assembly process here, getting everything in place. You go ahead and this axle pin is also 1/4-inch zinc plated rod that works very, very nicely with the bronze bushings. Everything fits nicely. And yeah, putting this one together is always a little bit of annoyance because there's so many parts that all have to be aligned and don't have enough fingers, and stuff is always falling out. And there we have it. Get it nice and tightened down, and That is a very, very nice, smooth bearing action here. And the next guy is going to be this steel magnet plate. And it's going to need a screw that isn't here, so back to the storage room again. Actually, I'm wrong. The screw was out here. I really should pre-position all of my screws, but I think I already said that. It's really nice putting together precision machine parts where everything fits, all the screw holes line up. Don't need to do any adjustment or modification. Everything just fits. So now I'm going to press a bearing, a bronze bushing into this block. And there's a little bit of a story behind this. This is the improvement that was made in the version 2.2. Using a socket as a spacer here to press the little bushing in place. The earlier versions had a short screw going into a tapped hole to be the axle for the twist axis, and that resulted in, they were usable, but I really didn't like the amount of slop they had. So in version, I think it was 2.2, I lengthened the axle. So now the axle is 1.5 inches long, and it screws into a recess, so it goes fairly deep into the aluminum part and the steel part, and this of course holds a lot of the axle in place, so I'm not just relying on the screw thread and the shoulder. I've actually got a substantial amount of precise metal-to-metal contact as a support. And then I added a spacer to lengthen the amount of area between two bushings, and the combination of all of that makes for a much more secure twist axis. So everything fits together so perfectly. I just love precision work. And there it is. Twist axis in place. Everything is nice. I use 1/4-20 shoulder screws, or not shoulder screws, socket screws, 1/4-20 socket screws to attach the springs. And a nylock nut on the far end to keep it from getting loose. Every time I look at the assembly and touch it, I'm inspecting for grease or Loctite or chips or contamination that might scratch up the nice surface, because I like them to look nice when they leave here. Of course, I also realize they don't look nice for long when they get out in the real world. But at least they look nice when they leave the shop. So there we have the spring retaining screws. I'm going to put a piece of cardboard over the base. I have two different strengths of spring, what I call the normal and the strong. The normal, for most glass workers, for most glass pieces, the normal spring is strong enough, but for people that make the really big stuff, the strong spring is definitely a benefit. And of course, because there's two springs, you get the extra kind of like bonus adjustment ability to be able to choose two normals, a normal and a strong, or two strongs. And of course, if you really want to get fancy, there are probably other spring options, weaker and stronger, that you could find out in the industrial world. So there we have it. Now I'm going to grab a couple of motors. Off camera, I mounted the main bearings into the bearing plate, and I didn't do a press fit on those bearings. I did a slightly tight slip fit and then used green Loctite, high temperature green Loctite bearing retaining compound number 620, and it does a really, really good job of holding these bearings in place. I've never had a problem with one. Yeah, I probably could do just a regular press fit, but the Loctite works really, really well, and I don't know, why change it if it works? Back to the storage room. The motors are from a Japanese company called Oriental Motor, and they are exceptionally high quality motors. I avoided using the El Cheapo no-name Chinese motors and picked the premium motors. Motors are important in this machine. The Oriental motors are the most expensive component, most expensive purchased component in the entire design. And Oriental motor, they're used in industrial automation. I used to work in the industrial automation business, and we used lots of Oriental motors. So don't skimp on quality. These guys cost about 3 times what the El Cheapo no-name Chinese motors, but they're great motors. When I first started the project, I used much smaller underpowered motors, and the most common comment I got from glass workers is, I need more power, I need more power, I'm stalling out the machine. And you know, as you apply paddle pressure or get a a piece that's maybe a little bit off center, some heavy solid chunk, big marble, big piece of marine prep. Good to have the motors. And these are the most powerful motors that are available in this case size, the NEMA 17 case size. The next size up is a NEMA 23, which are gigantic. And of course, this entire project has been a balance between, oh, I want more power, but more power means bigger, more power means heavier. Oh, a heavy head is hard to move around, it gets in the way. So I'm trying to keep things as light as they can be to make it easy to move them around, but still have sufficient power to get the job done. Always a trade-off. Always a trade-off. A little more Loctite. This operation is a tiny bit annoying as well. Maybe someday I need to figure out a super duper fixture to hold it in place. But I'm usually able to successfully complete it, so there we go. Motors are in place. Now these brackets have a little protruding prong with a hole for a set screw, and these are also used for precisely adjusting the perpendicular position. So between these two set screws, these two sets of set screws, you can get reasonably perpendicular. I mean, it's not a, it's not a machine tool, so don't expect to be within thousandths, but you can get pretty darn good precision, certainly good enough for glassworking, by using these alignment screws. So there we are, and we're ready for axles and drive rollers. Drive rollers are also held in place with set screws. Now, the axle is a kind of a slightly tricky little design, not that tricky, but slightly. I didn't show this on camera because it wasn't that interesting and I was too lazy to set up the camera. It's simply, the shaft, the motor drive shaft is 3/8 steel, zinc plated from the manufacturer, and the hole is 5 millimeter for the motor, and if I simply tapped a hole into the piece of metal itself, wouldn't get very many threads. So I got a commercially made shaft collar and fastened it to the shaft with the 620 green Loctite retaining compound, and the shaft collar came drilled and tapped for 1032. So after the Loctite had cured, I put it in the mill very precisely, poked a hole down, and then using the existing threads in the shaft collar, kind of followed the threads down with a 1032 bottoming tap. And this results in about 1/4 of an inch of good solid thread in the axle that holds really, really well. So, get some more set screws ready for the drive rollers. I actually like the Brits call them grub screws, and I think that's a far more humorous description. Let me go ahead and just lube up a bunch of these. Every screw gets Loctite unless it's a nylock screw. The original version of the NQALHA had 6 drive rollers, and it was fine. 6 drive rollers were useful, but people asked me, hey, what if I want to grip a really, really, really short little piece of glass, like a little 4-inch piece? Well, doesn't make it all the way to the end. It doesn't make it all the way to the far end, and so there's nothing there to grip it. So I added an extra couple of drive rollers. So the drive roller geometry, you've got rollers on both ends for controlling a long piece. Then there's another set of rollers close to the front of the unit that allow a space for the lock collar to ride. And then immediately after that, in between that roller and the clamp bearings, I put another roller. So you've got a roller, a clamp bearing, and a roller, and that allows a very short piece to be held in place. So set screws are in. Time for O-rings. The O-rings are a standard catalog item at McMaster Carr. So if you ever break one, or just wear it out, or set it on fire, they are high temperature silicone, so it's unlikely that you're gonna set them on fire. But they're standard catalog items, and I don't know if you can see here. Let me get the head out of the camera view. They're reasonably easy to stretch in place by hand with no special tooling. These are square profile, so they have a fairly good amount of much more gripping area, much more surface area than a round profile, which is what I used in the very first prototype so long ago. These are square profile, high temperature silicone, readily available. The design intent of the machine is to make it possible to do a lot of field repair without having to box the unit up. It's a heavy unit, pain in the ass to ship. And I want people to be able to maintain them on their own without having to constantly box them up and ship them home for work. And so many of the components are field replaceable using simple tools. So break an O-ring, no problem. All it takes is a few screws and a little bit of manual skill. The O-rings are, their nominal size is 1/8 inch, but their actual dimension is a little bit more. And when I cut the slot on the drive rollers using the CNC lathe attachment, I cut the thing in 2 passes with an 1/8 inch cutter to leave that little bit of extra. It's like 10/1000ths oversized, like a 135 instead of a 125. So the O-ring fits very, very nicely. Very, very nice fit. So the stepper motors have flats on them, and I line up the set screw with the flat. You probably can't see it on camera. I don't have a camera operator available to do all of the proper close-ups, but hey, you can imagine what it's like to line up a flat with a set screw. Then we just stack them up. Even though adding the extra 2 drive wheels results in a little more work, I think it's a valuable thing, and I think glassworkers do appreciate it, so got no problem adding it. And by the way, the current price on the NQALHA is still unchanged from version 1. So all of the enhancements, look at that, how perfectly everything just drops on and fits, lines up perfectly. I love precision work. So all the added expense for all the various different enhancements to the design, and while I'm talking and making mistakes, I forget things, so I need to put in the spacers, because as I've said before, bearing races, the bearing race is at the same level as its outer race is at the same level as its inner race, and the if there wasn't a spacer in there, the drive roller would bind against the bearing. Get a couple of little spacers. So anyway, to finish the thought that I was in the middle of, I basically eat the extra cost in all of these enhancements so I can keep the NQALHA affordable. I think I mentioned in other videos that this kind of small market work where you're building these in very small quantities, and there's a lot of not only machined parts but electrical parts, wood parts. A commercial shop, a commercial prototype shop, like the places that used to hire me, would charge $20,000–$30,000 a piece for one of these things after $500,000 in R&D. And I try to keep them affordable for glass workers. So, time to mount the cable harness. And I need to go get a screw. The wires kind of like turn around a corner here. And in the early versions, I kind of expected that they would just behave themselves and stay in place, but no, they didn't. And this loop started heading out and becoming out of control, so I made this little cover that kind of keeps the wires a little bit more under control, and works really well. The little guy's kind of a pain in the ass to make, but works really well. Does the job. So, I don't know if you can see it on the camera, but there we have the wire cover in place, and I'm going to tighten that down. The conduit routing on this guy was a bit of a trick, getting it all to work. And one of the kind of the keys to making it work was putting in this little piece of aluminum. You see it right there. This little piece of aluminum kind of keeps the conduit under control as it flexes around. As any robotic engineer knows, and yes, I've done a lot of work on robots, cable routing and cable flexing is one of the more difficult problems that we face, because wires don't like twisting like this. They prefer to bend like that. You bend a wire like that, it's going to bend all day. You start twisting it and you might end up with problems. These are the custom-made conduit clamps that I showed in a previous video, and yeah, sure would be convenient if I could find a commercial source for them and not have to make them, but haven't really found one yet. Well, the custom-made ones just work better. And they look nice, too. I mean, I might be able to find a commercial one that worked, but it'd probably be really ugly and mess up the clean lines of my design. Drop a Loctite. And I'll do the final adjustment of everything after it's fully assembled. Make sure that all the flex of the flex tube all flexes nicely and there's no binding and everything works well. So bend the ears of this guy over a little bit, make it fit nice. And there we have it. This is a guide that helps keep the conduit routing and flexing under control. And yes, assembly can be a tiny bit annoying with only two hands trying to hold everything in place. So there is that, and now I need to fish the cable through the horizontal arm. So I got a little wire with a hook on the end. And hook the little connector and pull him through. Then attach to the circuit board. And the end of the conduit has been epoxied into a little holding block. So and that is fastened into place with a screw. And of course everything fits really nicely. I love precision work. the adjustment of this. I do it just a little bit at a time. Got to get every bend just the right amount of bend to avoid binding. Get another clamp in place here to keep it from going crazy. Then I got another special tool, not that special, it's just a piece of bent wire, and I'm going to use that to fish these guys around the axle. Probably not strictly necessary, but I think it makes for a little bit cleaner of an installation. And yeah, this one is a bit of a geometric pain, but and sometimes it doesn't work. So try it again. Like so many things in this project, I probably could invent a better tool, a better technique, but this works. It's a tiny bit annoying, but you know, it does work. Sometimes it takes a couple of tries, unfortunately. It's a weird geometry. And yeah, every time I do one of these, I think, wonder if I could come up with a better idea. And then, of course, you know, it's just like the law, it's almost like the law of video, that it always goes worse when the camera's running. I do 10 of these in a row and they work perfectly. Then I turn on the camera and it takes me 3 tries to get one to work. So there we go. These wires are now properly routed. Circuit board fits the circuit board bracket. And I always leave my wires just a little bit long. Give a nice service loop for maintenance. Come on, little screw. Yep. Must be a law of video. When I'm doing this off camera, I drop a lot less screws. So, here's a handle assembly that got the lever feeling real nice, got the service loop in the wiring, so that if it's ever necessary to get at the circuit board again, it's easy. So, a little Loctite on the screws. that in place. Here's an extra special long hex driver that I use for this one because it's possible to use the regular length, but this just makes it a little bit easier. And grab a power supply. And just like the motors, I chose premium power supplies. They're made in China, but they're high quality Chinese parts. They're from a company called Meanwell, which is a rather strange name for an electronic company, but they're respected throughout the industry as being the quality stuff. So get the main connector in place, and I'm just about ready to start installing magnets now. To apply power, and there we go. First magnet in place. Second magnet in place, so I don't need the clamps anymore. It's holding position. And then with the magnet energized against the plate, I wiggle the little spring guy to make sure that the magnet bracket is parallel to the plate and the magnet is sitting nice and happy. And then tighten the retaining screw. Yep. It's looking good. Okay, so magnets work correctly. I'm getting ready to assemble the clamp, getting all the parts together. Off camera, I glued some rubber pieces to the aluminum and then cut them with a X-Acto knife into the proper shape. And now I'm collecting all of the pieces necessary to assemble a clamp. Okay, I got the parts here. I grease the sliding portions of the cam-operated clamp with some high-temperature grease. think this stuff is commonly used in automotive brakes, and it claims on the can to be usable up to 1,000 degrees, and haven't had a problem with one in the NQALHA. Put in a couple of springs. Hopefully everything will fit just fine. This is one of the, oh yeah, everything fits just fine. This is one of the more precise assemblies where the parts have to be machined to a fairly tight tolerance within a couple of thousandths. And it looks like these parts are correct. Everything is going nicely. The clamp should slide very freely. Let me get this. Okay. Putting some Loctite on the screws. The clamp should slide very freely because often when it's being used, the glass worker is usually doing more than one thing at one time and doesn't want to have to fight the clamp. And so it's good that it moves very freely, but then when it clamps, it's good that it clamps securely. So it slides very freely on the bar, no problem. All is well. Now, these little guys are the bogies, and onto the bogies go a couple of bearings, and I've got a little boss machined into the surface, because as I've said many times for many of these parts, that you can't just have a flat surface up against a bearing, because the inner race and the outer race are at the same level, and if you screw them tight up against a solid surface, you'll end up binding, and we certainly don't want binding. So, got the Loctite on. The flathead screw kind of automatically centers the bearing in its proper location and doesn't protrude a lot outside the periphery of the bearing. I don't want excessive protrusion because the area where the bearing goes is a kind of a tight little spot. So the flathead screw works perfectly for this. When I was making the part, this, what I call the bogie, the aluminum part, I wanted to make sure the material comes in a little bit. Sometimes it's an extrusion, it comes in all over the place, but it often comes in a little bit too thick, and the pivot point of this is going to be a shoulder screw, and if the shoulder screw, when it's tightened, if the material is a little bit thicker than the length of the shoulder, you get binding. So that's another reason why I mill down the material a little bit, so I prevent binding on the shoulder screw, and at the same time get that little bit of relief for the bearing bosses. So this is a left and right assembly, so I have to make sure to assemble them on the correct side. Totally free, no binding, and the same thing applies to the clamp arms, that they are machined slightly to make them just a little bit thinner, make them a few thousandths undersize, so that when the screw is tightened, they get a little bit, just the smallest amount of resilience here. And while I'm talking, I put this one on backwards, so talking and working. I make a lot more mistakes when I'm talking. What I don't want to do is clamp glass between really solid metallic clamps. Glass doesn't like being clamped between solid metallic clamps, and so I have two strategies. First of all, the O-rings have resilience, and second of all, the clamp arm has this little pivot point and a little bit of a rubber bumper here. I probably could just make the thing solid and not use the rubber bumper, and it would probably work just fine. But I am concerned about not cracking glass in the machine, so I put the little bit of extra effort into the shoulder screw, the little rubber bumper, and machining the reasonably complex little end shape there, all to allow a tiny bit of resilience. And parts continue to fit together extremely well. I love precision work. And then there's one more little part. It's a little steel part. And this was not part of the original design. It was a kind of a retrofit, but it seems to fit nicely. It almost looks like it was intended to be that way. It's a little steel part that attaches to the top of the clamp, and there it is, right there, little chrome steel part. And that guy sticks to the magnet, which attaches up here, so that when you want the clamp to just hold its position at the top without clamping the clamp lever, you just pop it up to the top and it sticks, which is a very convenient thing that works really well. That's new in version 2.2. So I do continue to evolve and perfect the design. I use an NQALHA a lot in my own glass work, and I'm constantly looking for ways to refine and perfect it, but the design is working pretty darn well, and kind of running out of things to perfect. So got another long screwdriver and a slightly tricky little assembly. Everything is easier once the magnets are mounted. So, now that I have the clamp in place, and let me do one last little adjustment here. A fairly tight fit, and I like it that way. I like it to be tight and precise. It won't come apart. So now I'm going to position the rollers. Let me get a clamp handle and a screw. The clamp handle can be repositioned at any angle that the, any angle within reason, but any angle that the glass worker wants. Yeah. Nice and smooth. Clamp design works really well. Get my little ball driver. The lever is intentionally a hair trigger because I think a lot of people like it that way. Kind of gets tiresome to have to crank a heavy spring-loaded lever, but of course that means that if I bump into it while I'm working, the magnets release. So getting the screws into place, and this is a ball end hex driver, and it works really well, but it doesn't quite have the power of a regular hex. Set screws on the drive rollers are nice and secure. I don't want them coming loose, so I give them that extra little fraction of a turn with a regular hex key. Not much. Don't want to get too crazy. It's only aluminum. But nice to have them just a little bit tighter. The ball end drivers work really, really well, but if you really want the most clamping force, you kind of need to use the old school hex wrench. Okay, so now with my motor wiring pieces and connectors in place, and this guy is almost finished. The very first NQALHA version 2.3. And in keeping with the tradition here of everything works worse on video, I have a wiring error in this motor connector. Nothing difficult. Takes a minute to fix it, but it's the first time I ever made that mistake. Must be because I'm on camera. So, motors work correctly. I'll get a thumb wheel and a grub screw. Wipe off the little excess bit of Loctite, and wow, it's an NQALHA. Here's a new design for version 2.3. It's a heat sink that is designed to dissipate a little more heat from the motor drivers. The new 2.3 design has a slight modification to the housing, the controller housing, as well as an additional little piece of aluminum that act to come in solid contact with the motor driver chip and its circuit board, and then transfer the heat into the aluminum body of the controller housing and its heatsink. So everything is working very nicely. It feels really smooth, moves around really nicely. The vertical axis feels very nice. Lever feels very nice. All operation appears correct. Now I'm gonna put the last part on, the aluminum heat shield. And just a little comment about the heat shield. this part of the controller where the encoder is, and the push buttons, the encoder is actually an active electronics, and it doesn't want to overheat. And also, this is where your hand is, and you certainly don't want to overheat your hand. And so it's a really good idea to have this aluminum heat shield that is mounted to the side. Now, some glassware, I just made this shape. It seems like a reasonable shape and it seems to work well, but other glass workers have different ideas, and it's just sheet metal. If you have the ability to cut and drill sheet metal, you can either modify the one that comes with the NQALHA or make your own. As long as you cover the hand and the electronics, you can pretty much make any shape you want. So that, I'm waiting for the Loctite to cure on the little magnet, so I can't assemble that. And then I'm going to put some cable ties on it and just kind of clean it up and shine it up and clean it and take a picture of it. So that is probably all that I'm going to show of the assembly. I've got a couple of more things. I'm going to put on some cable ties and adjust all of the conduit routing and make sure that all the there's no pinching and that everything seems to be working correctly. Then I'm going to run the thing for 2 days, 24 hours a day. A lot of times when electronic equipment fails, it'll fail within the first few hours of use. The most likely time for an electronic component to fail is the first time power is applied. In the industry, it's referred to as infant mortality. And if you look at the graph of failure over time, it looks kind of like that. And it's kind of like if your piece of electronics lasts for a few days, it'll likely last forever. And so I run every one of these for a couple of days constantly just to make sure all is well. And this has been the assembly of the very first ever NQALHA version 2.3 from Production Run 4. And I've got 9 more to assemble, so got a lot of work ahead, but this will be the last video in Series 4. Thank you for watching. I hope you found it interesting. And if you're a potential NQALHA user, I hope you find my invention useful. I hope you make a lot of amazing glasswork with this machine. Thank you again.